Everything that exists was once compressed into a space smaller than a single atom. Not most things, not a large fraction of things. Everything, every galaxy in the observable universe, every star, every planet, every moon, every asteroid, every atom of gas drifting in the void between galaxies, every particle of dark matter, every quantum of energy, every photon of light. All of it, the entire contents of a universe containing 2 trillion galaxies, compressed into a region of space so unimaginably small that the word microscopic does not begin to describe it. And then, in a moment that had no before, in an event that was not an explosion in space but an explosion of space itself, it expanded. Not slowly, not gradually. In the first second after that expansion began, the universe underwent changes so extreme, so violent, so fundamentally transformative that the physics required to describe them pushes the very limits of what human mathematics can handle. In the first second, the universe went from a temperature of 10 to the power of 32 degrees, a number so large that writing it out would take more digits than there are atoms in your body, to a temperature of 10 billion degrees. In the first second, the fundamental forces of nature separated from a single unified force into the 4 distinct forces we know today. In the first second, the matter and antimatter that were produced in almost equal quantities annihilated each other in the most violent process the universe has ever seen, and by a margin of 1 part in a billion, matter won. That margin, that 1 extra particle of matter for every billion that annihilated, is the reason you exist. In the first second, the universe decided what it was going to be. And what happened in that second is one of the most extraordinary, most violent, most strange stories in all of science. Before we enter the first second, we need to address the question that everyone asks. What came before the Big Bang? The honest answer is, we don't know. And the reason we don't know is more interesting than any speculative answer could be. The Big Bang was not an explosion that happened at a point in space, the way a bomb explodes. Space itself did not exist before the Big Bang, or rather, the concepts of space and time as we understand them break down at the earliest moments. Einstein's general relativity, our best theory of space, time, and gravity, predicts that if you run the universe backward in time, tracing the expansion in reverse, you arrive at a singularity. A point of infinite density and infinite temperature where the equations break down completely. Just as with the singularity at the center of a black hole, infinite is not an answer. It is a confession that the theory has reached its limit. General relativity cannot describe what happens at the Big Bang singularity. Neither can quantum mechanics. A complete description would require a theory of quantum gravity, a theory that unifies general relativity and quantum mechanics. And as we have discussed in previous videos, we don't have one yet. So the question of what happened before the Big Bang, or what caused it, is genuinely unanswerable with current physics. Some theories propose that time itself began at the Big Bang, that asking what came before is like asking what is south of the South Pole. There is no before. Time is a property of the universe. Without a universe, there is no time. Without time, there is no before. Others propose a cyclic universe, a big bounce, where our Big Bang was the rebound from a previous universe's collapse. Others propose that our universe nucleated from a quantum fluctuation in a pre-existing space-time. Others propose eternal inflation, in which our Big Bang was the formation of a bubble in an eternally inflating background. All of these proposals are speculative. None is confirmed. What we know begins not at the singularity, but slightly after it, at a moment called the Planck time, 10 to the power of negative 43 seconds after the beginning. 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second. Before the Planck time, the energy density of the universe was so extreme that quantum gravitational effects dominated, and without a theory of quantum gravity, we cannot describe this era. It is a wall of ignorance, the earliest moment our physics can reach, and from that wall onward, we begin to understand what happened. At 10 to the power of negative 36 seconds, the universe underwent the most extreme event in its history. More extreme than any supernova, more extreme than any black hole merger, more extreme than anything that has happened in the 13.8 billion years since. In a period lasting from approximately 10 to the power of negative 36 seconds to 10 to the power of negative 32 seconds, a duration so brief it makes a nanosecond look like an eternity, the universe expanded exponentially. Not by a factor of 2, not by a factor of 1,000,000, by a factor of at least 10 to the power of 26. The universe grew by at least 100 million billion times in size, in a fraction of a fraction of a fraction of a second. To put this in perspective, if a single atom expanded by the same factor as the universe did during inflation, it would end up larger than the observable universe. This extraordinary event is called cosmic inflation, and it was not driven by the ordinary expansion of space. It was driven by the energy of a quantum field, called the inflaton field, that was temporarily stuck in a high-energy state, generating a repulsive gravitational effect that caused space itself to expand exponentially. Why does inflation matter? It solves 3 deep problems in cosmology that had puzzled physicists since the Big Bang theory was developed. The first is the horizon problem. The universe looks extraordinarily uniform in every direction. The temperature of the cosmic microwave background is the same to 1 part in 100,000 in regions of the universe that are so far apart they could never have been in contact with each other at the speed of light. How did they reach the same temperature if they were never connected? Inflation answers this by saying they were connected. Before inflation, the entire observable universe was a tiny region, small enough for thermal equilibrium to be established. Inflation then stretched this region to cosmic scales, preserving the uniformity. The second is the flatness problem. The universe is geometrically flat. The angles of large cosmic triangles add up to exactly 180 degrees, with extraordinary precision. For the universe to be this flat today, it must have been flat to a precision of 1 part in 10 to the power of 60 at the time of the Big Bang. Inflation explains this naturally. Any geometry, stretched by a factor of 10 to the power of 26, becomes effectively flat, the same way the surface of the Earth appears flat to someone standing on it. The third is the magnetic monopole problem. Grand unified theories predict that magnetic monopoles, isolated north or south magnetic poles, unlike the dipoles of ordinary magnets, should have been produced in abundance in the early universe. We have never detected one. Inflation dilutes any magnetic monopoles produced before or during inflation to such a tiny density that the probability of one being in the observable universe is negligible. 3 problems. 1 solution. But inflation did something else, something that connects directly to the large-scale structure of the universe and to the existence of everything in it. It took quantum fluctuations, tiny random variations in the inflaton field, and stretched them to cosmic scales. Those quantum fluctuations became the seeds of everything. The tiny density variations that inflation imprinted on the early universe, variations of 1 part in 100,000, are the seeds from which every galaxy, every star, every planet, every living thing eventually grew. Your existence traces back to quantum fluctuations that were stretched to cosmic scales in the first fraction of a second of the universe's history. From the Planck time, 10 to the power of negative 43 seconds, to approximately 10 to the power of negative 36 seconds, the universe existed in a state that no human has ever experienced, and that no experiment has ever replicated. This is called the Planck era. In this era, the universe was so hot, so dense, so energetic that all 4 fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into a single force. The 4 forces that govern everything in the universe today, the gravity that holds galaxies together, the electromagnetism that makes chemistry possible, the strong force that holds atomic nuclei together, the weak force that governs radioactive decay, were not 4 separate things. They were one. A single unified force, operating at energies so extreme that the distinctions between them were meaningless. We call this hypothetical unified state the theory of everything, and we do not have it. We have tantalizing hints: string theory, supersymmetry, loop quantum gravity, but no confirmed, tested theory that describes physics at Planck energies. What we do know is what happened next. As the universe expanded and cooled, the unified force began to separate. The process is called symmetry breaking. When the temperature drops below a critical threshold, a symmetry that was present at higher energies is broken, and what was one force becomes 2. The first separation, gravity splitting from the unified force, occurred at the Planck time itself, 10 to the power of negative 43 seconds. The second separation occurred at approximately 10 to the power of negative 36 seconds. At this moment, the strong nuclear force split from the electroweak force, the unified combination of electromagnetism and the weak force. And this second separation triggered something extraordinary, something that would shape the entire history of the universe: cosmic inflation. When inflation ended, when the inflaton field finally released its energy, something extraordinary happened. All the energy stored in the inflaton field converted into a hot, dense plasma of fundamental particles. The universe went from the cold, empty, exponentially expanding void of inflation to a screaming, billion-degree fireball of matter and energy. This process is called reheating, and it happened with extraordinary violence. The inflaton field oscillated rapidly, decaying into pairs of particles and antiparticles, quarks, antiquarks, leptons, antileptons, photons, and the carriers of the fundamental forces. In an almost incomprehensibly brief time, the universe was filled with a dense, hot plasma of every type of particle that physics permits. The temperature after reheating reached somewhere between 10 to the power of 15 and 10 to the power of 25 degrees Kelvin, depending on the specific model of inflation. Hot enough that the energies of individual particles far exceeded anything achievable in the Large Hadron Collider. The universe was a particle accelerator of incomprehensible power. And in this fireball, the fate of everything was being decided. Here is the most important thing that happened in the first second of the universe, and the most mysterious. When energy converts to matter, when a photon produces a particle, it always produces a particle and its antiparticle simultaneously. Matter and antimatter created in equal pairs. This is not a rule that physicists imposed. It is a consequence of the deep symmetries of physics. For every electron created, a positron. For every quark, an antiquark. For every particle, its mirror image of opposite charge. If the universe obeyed this symmetry perfectly, if matter and antimatter were produced in exactly equal quantities, then as the universe cooled and particles met their antiparticles, they would annihilate. Every particle would find its antiparticle. The annihilations would be complete. The universe would contain only photons, only light. No matter, no stars, no planets, no chemistry, no life. But we exist, which means matter won. Somehow, somewhere in the first fraction of a second, the symmetry between matter and antimatter was broken. More matter was produced than antimatter, or antimatter was destroyed preferentially, by some process we do not fully understand. The excess was tiny. For every 1 billion antiprotons in the early universe, there were 1,000,000,001 protons. One extra proton for every billion pairs. That tiny excess, 1 part in a billion, is everything. Every atom of ordinary matter in the universe, every star, every planet, every living thing. All of it is the 1 in a billion survivor of the great matter-antimatter annihilation. The process that created this asymmetry is called baryogenesis, and it remains one of the deepest unsolved problems in physics. We know it happened. We are living proof that it happened. But we do not know how. The physicist Andrei Sakharov, one of the fathers of the Soviet hydrogen bomb, who later became a dissident and human rights activist, identified in 1967 the 3 conditions that any successful theory of baryogenesis must satisfy. They are called the Sakharov conditions. First, baryon number violation. The number of baryons, protons and neutrons, must be able to change. There must be processes that create more matter than antimatter. Second, C and CP violation. The laws of physics must treat matter and antimatter differently. This has been observed in certain particle decays. CP violation is real, but the amount observed in the standard model is far too small to account for the matter-antimatter asymmetry we see. Third, departure from thermal equilibrium. The universe must pass through a period of being out of thermal equilibrium, a phase transition, a rapid change in conditions, during which the asymmetry can be generated. The standard model of particle physics satisfies all 3 conditions in principle, but not sufficiently. The CP violation in the standard model is too small. The electroweak phase transition is not violent enough. Something beyond the standard model, some new physics, must be responsible for baryogenesis. We don't know what it is. We know only its consequence. At approximately 10 to the power of negative 12 seconds after the Big Bang, 1 trillionth of a second, the universe crossed another threshold. The temperature dropped below approximately 100 billion degrees, and the Higgs field switched on. The Higgs field, whose quantum excitation is the Higgs boson, discovered at CERN in 2012, pervades all of space. In the very early universe, it was in a high-energy symmetric state. Particles interacted with it weakly. The electromagnetic force and the weak nuclear force were still unified as the electroweak force. At this moment, at the electroweak phase transition, the Higgs field dropped to its low-energy state. It began interacting strongly with certain particles, and in doing so, it gave them mass. Before this moment, all fundamental particles were massless. They moved at the speed of light. After this moment, the particles that interact with the Higgs field acquired mass. The W and Z bosons, the carriers of the weak force, became massive, while the photon, the carrier of electromagnetism, remained massless. The electroweak force split into electromagnetism and the weak nuclear force. And the particles of matter, quarks and electrons, acquired their masses. The masses that determine chemistry, the masses that determine the structure of atoms, the masses that determine the properties of everything made of ordinary matter. Without the Higgs field switching on at this moment, atoms could not form. Chemistry would be impossible. Life as we know it could not exist. The Higgs mechanism, the process by which the Higgs field gives mass to particles, is one of the most profound and beautiful pieces of physics ever discovered. It was proposed theoretically in 1964 by Peter Higgs and others. It was confirmed experimentally by the discovery of the Higgs boson in 2012. But at 10 to the power of -12 seconds, it was not a theoretical prediction or an experimental discovery. It was reality, switching on. For the first microsecond of the universe's existence, protons and neutrons did not exist. The building blocks of atomic nuclei, the particles that make up everything you have ever touched, had not yet formed. Instead, the universe was filled with a quark-gluon plasma. A hot, dense soup of quarks and gluons, the fundamental constituents of protons and neutrons, moving freely through space, unconfined, interacting with the strong nuclear force in a state that has existed nowhere in the universe since. Nowhere, except briefly, for tiny fractions of a second, in the most powerful particle collider ever built. The Large Hadron Collider at CERN has recreated quark-gluon plasma by colliding lead nuclei at extraordinary energies. The droplets of quark-gluon plasma produced in these collisions last for approximately 10 to the power of -23 seconds before cooling and forming ordinary hadrons. They are the hottest objects ever created in a laboratory, hotter than the center of the sun by a factor of hundreds of thousands, and they give us a tiny window into the universe as it existed in its first microsecond. At approximately 1 microsecond after the Big Bang, 1/1,000,000th of a second, the universe had cooled enough for a process called quark confinement to occur. The strong nuclear force has a remarkable property. Unlike gravity or electromagnetism, which weaken with distance, the strong force between quarks actually increases with distance, up to a point. Trying to pull a quark away from its partners is like stretching a rubber band. The further you pull, the stronger the force pulling back. And if you pull hard enough, instead of separating the quarks, you create new quark-antiquark pairs from the energy of the stretching. The quarks can never be isolated. At 1 microsecond, the quark-gluon plasma cooled below the confinement temperature. Quarks, previously free, bound together into composite particles. Hadrons. 3 quarks bound together to form baryons, protons and neutrons. A quark and an antiquark bound together to form mesons, short-lived particles that no longer exist in significant quantities in the universe today. In the first microsecond, protons were born. The building blocks of all ordinary matter in the universe, every nucleus of every atom of every element, formed in that single microsecond. From 1 microsecond to approximately 1 second after the Big Bang, the universe was a sea of protons, neutrons, electrons, positrons, neutrinos, and photons, all in thermal equilibrium, all interacting frantically with each other at temperatures of trillions of degrees. In this environment, protons and neutrons were constantly converting into each other through weak nuclear reactions. A proton could absorb an electron neutrino and become a neutron. A neutron could emit an electron neutrino and become a proton. The balance between protons and neutrons was determined by temperature. At very high temperatures, the conversion reactions were rapid, and the ratio of neutrons to protons was close to 1:1. But as the universe cooled, the weak reactions slowed. At approximately 1 second after the Big Bang, when the temperature had dropped to about 10 billion degrees, the weak reactions became too slow to maintain equilibrium. The neutron-to-proton ratio froze at approximately 1:7. For every 7 protons, there was 1 neutron. This ratio, determined in the first second, is one of the most important numbers in the history of the universe, because it determines the composition of the universe that emerged from the Big Bang. It determines how much hydrogen, how much helium, and how much of the heavier elements were produced in the first few minutes. At 1 second, the universe crossed a threshold. Neutrinos, which had been interacting with matter through the weak force, became effectively free. The universe was transparent to neutrinos. They decoupled from the rest of the matter and energy, streaming freely through space. Those neutrinos still exist. Right now, approximately 336 cosmic background neutrinos pass through every cubic centimeter of space, through your body, through the Earth, through everything, at nearly the speed of light. They are the oldest particles in the universe, relics of the first second. We have never directly detected them. They interact so weakly that no detector yet built is sensitive enough. But we know they are there. The mathematics of the early universe demands it. From 1 second to approximately 3 minutes after the Big Bang, the universe underwent a process called Big Bang nucleosynthesis. The temperature, still billions of degrees, was hot enough for nuclear fusion, but cool enough for atomic nuclei to survive once formed. Protons and neutrons began to fuse. A proton and a neutron fused to form deuterium, heavy hydrogen. Deuterium captured another proton or neutron to form helium-3 or tritium. 2 deuterium nuclei fused to form helium-4. The process was extraordinarily fast, all of it occurring within the first 3 minutes. And the neutron-to-proton ratio that froze at 1 second determined the outcome. With 1 neutron for every 7 protons, almost all neutrons ended up bound into helium-4. Each helium-4 nucleus contains 2 protons and 2 neutrons. With 1 neutron for every 7 protons, the helium-4 contains about 25% of the mass of ordinary matter. The remaining 75% stayed as hydrogen, single protons. Small amounts of deuterium, helium-3, and lithium-7 were also produced. And that was it. After 3 minutes, the temperature had dropped too far for further fusion. Nucleosynthesis ended. The universe's elemental composition was fixed. Approximately 75% hydrogen, 25% helium, tiny traces of deuterium, helium-3, and lithium-7. No carbon, no oxygen, no iron, no gold, none of the heavier elements. Those would have to wait for stars, nuclear furnaces that would form hundreds of millions of years later, fuse hydrogen and helium into heavier elements, and scatter those elements across the galaxy in stellar winds and supernova explosions. But the hydrogen and helium that forms the fuel of stars, that forms the vast majority of ordinary matter in the universe, was produced in the first 3 minutes. And the predictions of Big Bang nucleosynthesis, the precise abundances of hydrogen, helium, deuterium, and lithium produced, match what we observe in the oldest, most pristine regions of the universe, with extraordinary accuracy. This is one of the strongest confirmations of the Big Bang theory. The first 3 minutes of the universe, described by physics we understand reasonably well, produce exactly the elemental abundances we observe. The universe is telling us our story was right. For all the extraordinary understanding we have of the first second, the separation of forces, inflation, baryogenesis, quark confinement, the freeze-out of neutrinos, the fixing of the neutron-to-proton ratio, there are deep gaps that sit at the center of the most important questions in physics. We do not understand inflation at a fundamental level. We know it happened, the evidence is overwhelming. But we don't know what the inflaton field is, where it came from, or why it had the properties it did. Different inflation models make different predictions, and the observations needed to distinguish them are at the frontier of what current and near-future experiments can reach. We do not understand baryogenesis. We know the Sakharov conditions. We know that something beyond the standard model is required. But the specific mechanism, the new physics that produced the matter-antimatter asymmetry, remains unknown. It is one of the most important unsolved problems in particle physics. We do not understand what happened before inflation. The Planck era, the first 10 to the power of -43 seconds, is beyond the reach of any physics we currently possess. It requires a theory of quantum gravity that we have not yet built. And most fundamentally, we do not understand why there is something rather than nothing. Why did the Big Bang happen? Why does a universe exist at all? Why do the laws of physics have the form they do? These questions sit at the boundary of physics and philosophy. Some physicists believe they will eventually be answered by a complete physical theory. Others believe they are unanswerable in principle, that the existence of any universe at all is a brute fact, unexplained and inexplicable. The first second of the universe is the most information-dense second in the history of everything. More happened, more changed, more was decided in that 1 second than in all the 13.8 billion years that followed. And we understand it, partially, imperfectly, with deep gaps that represent the frontier of human knowledge. The universe began with a second of extraordinary violence and transformation, and we are still working out what happened. 1 second. In 1 second, in that extraordinary, violent, transformative first second, the universe decided everything. The forces that govern physics separated from unity into 4 distinct interactions. The Higgs field switched on and gave matter its mass. Quarks confined themselves into protons and neutrons. A tiny asymmetry between matter and antimatter, 1 part in a billion, ensured that something rather than nothing survived the great annihilation. In 1 second, the ingredients for everything were assembled. Not the finished products, not the stars, not the galaxies, not the planets, not the chemistry, not the life. All of that would take hundreds of millions of years, billions of years, to emerge from those ingredients. But the ingredients, the protons and neutrons and electrons, in the proportions determined by that first second, governed by the forces whose strengths were fixed in that first second, were set. And every atom in your body is a direct descendant of that first second. The hydrogen in the water you drink was produced in the first 3 minutes. The protons in your cells were born at 1 microsecond. The mass of every electron in every atom of your body was given to it by the Higgs field at 1 trillionth of a second. You are not separate from the Big Bang. You are its consequence, its most recent, most complex, most improbable consequence, but its consequence nonetheless. The universe began with a second of fire and transformation. It produced, eventually, creatures who can look back at that second and reconstruct what happened. That reconstruction is incomplete, full of gaps, full of unanswered questions that will occupy physicists for generations. But it exists, which means that the universe, in its first second, set in motion a chain of events that eventually produced the capacity to understand itself. And that, perhaps, is the most extraordinary thing about the first second of everything. Not the forces, not the particles, not the temperatures, the fact that it led, eventually here. To truly understand what happened in the first second, we need to understand what the 4 fundamental forces actually are, because the story of the first second is, at its heart, the story of how these forces came to be separate. Today we experience 4 distinct forces. Gravity is the weakest of the 4, by an almost incomprehensible margin. The gravitational attraction between 2 protons is approximately 10 to the power of 36 times weaker than the electromagnetic force between them. And yet gravity dominates the large-scale structure of the universe because it is always attractive, never repulsive, and accumulates over the vast masses of stars and galaxies. Electromagnetism governs the behavior of charged particles. It is responsible for the structure of atoms, the attraction between positively charged nuclei and negatively charged electrons. It is responsible for chemistry, the sharing and transfer of electrons between atoms that creates molecules. It is responsible for light. Photons are the quanta of the electromagnetic field. Without electromagnetism, there are no atoms, no chemistry, no light, no life. The strong nuclear force is the most powerful of the 4 at short ranges. It binds quarks together into protons and neutrons, and binds protons and neutrons together into atomic nuclei. Without it, nuclei would fly apart, repelled by the electromagnetic repulsion between their positively charged protons. Without the strong force, there are no nuclei, no elements, no periodic table. The weak nuclear force governs certain types of radioactive decay. It is responsible for the process by which a neutron converts to a proton, beta decay, and for the nuclear reactions that power the sun. It is weaker than the strong force and electromagnetism, but far stronger than gravity. 4 forces, vastly different in strength, operating over vastly different ranges, described by completely different mathematical frameworks. And yet, in the extreme conditions of the early universe, they were one. At sufficiently high energies, the electromagnetic force and the weak force unify into the electroweak force. This unification was proposed theoretically by Sheldon Glashow, Abdus Salam, and Steven Weinberg in the 1960s and 1970s, and confirmed experimentally with the discovery of the W and Z bosons at CERN in 1983. At even higher energies, the energies of the first 10 to the power of negative 36 seconds, the strong force unifies with the electroweak force into a grand unified force. We have theoretical models for this grand unification, but it has never been confirmed experimentally. The energies required exceed anything achievable in any accelerator we could build on Earth. And at the Planck energy, the energy of the first 10 to the power of -43 seconds, gravity unifies with all the others. The theory of everything. The single unified force from which all four emerged as the universe cooled. We do not have this theory. We have hints, string theory, loop quantum gravity, various approaches that have partial success and fundamental limitations. But we know it existed. The universe's behavior at the largest scales, the smoothness, the flatness, the structure, all point to a beginning in which everything was unified. The story of the first second is the story of that unity fragmenting, symmetry breaking, one becoming two becoming four, the universe differentiating from a state of perfect, featureless unity into the rich, complex, structured reality we inhabit. We touched on cosmic background neutrinos earlier, the ghostly particles that decoupled from ordinary matter at 1 second and have been streaming freely through the universe ever since. But they deserve a deeper look. Neutrinos are the second most abundant particle in the universe, after photons. For every proton or neutron in the universe, there are approximately 1 billion neutrinos. They pervade all of space. Approximately 336 cosmic background neutrinos occupy every cubic centimeter of the universe, moving in every direction at close to the speed of light. They are everywhere. They have always been everywhere since they decoupled at 1 second. And they have shaped the universe in ways we are still working out. In the early universe, before decoupling, neutrinos were tightly coupled to the photon-baryon plasma. They contributed to the pressure that resisted gravitational collapse. They affected the oscillations of the primordial plasma, the acoustic oscillations that left their imprint on the cosmic microwave background. After decoupling, they streamed freely, but they continued to affect the universe through their gravity. Neutrinos have mass, tiny, but non-zero, and their gravitational effect on the formation of large-scale structure leaves a detectable imprint on the distribution of galaxies and on the CMB. By analyzing the CMB and galaxy surveys with extraordinary precision, cosmologists have been able to constrain the total mass of all 3 types of neutrinos. The current upper limit is approximately 0.12 electron volts, far smaller than any other known massive particle. We have never directly detected a cosmic background neutrino. Their energies are so low, cooled by 13.8 billion years of cosmic expansion to a temperature of just under 2 degrees Kelvin, that they interact with ordinary matter almost never. A detector sensitive enough to detect cosmic background neutrinos would need to contain many tons of a specially chosen target material, cooled to temperatures near absolute zero, and run for many years in an environment shielded from every other source of background. Such a detector, called Ptolemy, has been proposed. It would use tritium as a target material, looking for the tiny recoil imparted to electrons when a cosmic background neutrino interacts with a tritium nucleus. The signal would be almost unimaginably small, but not impossible in principle. If Ptolemy or a similar experiment ever detects cosmic background neutrinos directly, it will be one of the greatest experimental achievements in the history of physics. A direct detection of particles produced in the first second of the universe. A direct observation of the Big Bang itself.